The Douglas F3D Skyknight wasn't just another jet, it was a game-changer in aviation history. Known for its exceptional 6:1 ratio during the Korean War, this aircraft became the most successful naval fighter of the conflict. But what truly set it apart was its groundbreaking design as the world's first jet-powered night fighter. With advanced radar technology capable of detecting enemies over 125 miles away, a unique cockpit layout for seamless crew communication, and twin engines delivering unmatched power, the Skyknight redefined air combat. In this video, we'll uncover the genius engineering behind this remarkable war machine and how it dominated the skies when it mattered most. Revolutionary radar integration in the F3D Skyknight. The Westinghouse AN APQ-35 radar system stood as the cornerstone of the F3D Skyknight's night fighting capabilities. This sophisticated system combined three distinct radars, each serving unique functions in the aircraft's mission profile. The AN APQ-35 radar system was a groundbreaking technological innovation that set the Douglas F3D Skyknight apart from its contemporaries. This sophisticated system integrated three specialized radar units, each designed for a specific purpose to enhance the aircraft's combat effectiveness. The AN/APS-21 search radar could detect fighter-sized targets at distances of up to 20 miles, offering long-range situational. Complementing this was the AN/APG-26 tracking radar, which enabled weapons lock capabilities at a range of up to 2.25 miles, ensuring precision targeting in high-stakes engagements. Adding another layer of defense, the AN/APS-28 tail warning radar provided rear protection by detecting potential threats within a 10-mile radius. These radar units worked in harmony to deliver unmatched functionality. The AN/APS-21 identified and tracked initial targets while simultaneously scanning for new ones, seamlessly transferring tracking responsibilities to the AN/APG-26 for precise targeting. Beyond its detection and tracking capabilities, the AN/APQ-35 also offered beacon interrogation for navigation and communication purposes, and could compute gun solutions for the Skyknight's 20mm cannons, optimizing accuracy in combat. This advanced integration of radar technology not only defined the Skyknight as a formidable night fighter, but also represented a significant leap in airborne electronic systems. The vacuum tube-based radar system, developed before semiconductor electronics, demanded intensive maintenance to maintain operational status. Notably, the radar operator managed three separate radar displays along with numerous controls and switches on the front console. The system's complexity posed significant training challenges, as the program initially lacked specialized instruction for radar operators. The integration of this advanced radar system substantially influenced the F3D's design. Primarily, the aircraft required a larger nose section to house both the AN/APS-21 and AN/APG-26 radar dishes. The F3D2 variant featured enlarged engine air intakes to accommodate increased airflow requirements. Consequently, these modifications affected the aircraft's aerodynamic properties, leading to the addition of a spoiler system for improved maneuverability. The radar system's effectiveness proved crucial in combat operations. While lacking the swept wings and high subsonic performance of contemporary fighters like the MiG-15, the F3D's superior radar capabilities enabled successful night interceptions. The long search range proved particularly valuable, with crews detecting numerous contacts beyond ground control intercept station capabilities. Innovative airframe engineering solutions. Douglas engineers crafted the F3D Skyknight's airframe with innovative solutions to accommodate its unique operational requirements. The aircraft's distinctive design emerged from careful consideration of crew coordination, engine performance, and carrier-based operations. The F3D featured an unconventional side-by-side seating arrangement, with the pilot positioned on the right and the radar operator on the left. First of all, this configuration enhanced crew communication and coordination during night operations. The cockpit incorporated a large, flat windscreen that, although not optimal for high-speed flight, provided distortion-free visibility essential for night operations. Instead of traditional ejection seats, the aircraft utilized an innovative escape system. The design incorporated an inclined tunnel behind the cockpit, accessed by rotating the crew seats. Moreover, the cockpit featured pressurization and air conditioning systems, along with a bulletproof windscreen in the F3D2 variant. The power plant configuration of the F3D Skyknight showcased meticulous engineering, designed to optimize performance and functionality. The aircraft was equipped with twin Westinghouse J-34 engines, each capable of generating 3,400 pounds of thrust, providing the power necessary for its role as a night fighter. These engines were mounted with a unique arrangement, canted downward and angled away from the aircraft's body. This distinctive positioning not only enhanced stability, but also reduced the risk of damage from engine exhaust gases. Additionally, the engine nacelles were seamlessly integrated into the lower fuselage, contributing to the aircraft's aerodynamic efficiency and compact design. As a result of this configuration, the aircraft required specialized cooling systems. The engine placement demanded careful thermal management, as demonstrated by the 15 to 20-minute idle time required on carrier decks. Similarly, the F3D2 variant received enlarged nacelles to accommodate more powerful J-34 W36 engines. The F3D adaptation for carrier operations necessitated substantial structural modifications. The aircraft incorporated robust landing gear with a hydraulic retraction system, supplemented by a pneumatic backup system for emergencies. The wing design featured two-spar construction with slotted flaps and ailerons, later enhanced with spoilers on the F3D2 to improve maneuverability. The control system employed hydraulic boosters with rigid control wiring, ensuring reliable operation in demanding carrier environments. The aircraft also featured an analog automatic control system, G3 autopilot, later complemented by an automatic carrier landing system introduced in 1957. Advanced electronic systems integration. The electronic systems integration in the F3D Skyknight marked a significant advancement in naval aviation technology. Primarily designed for night operations, the aircraft incorporated sophisticated electronic warfare capabilities that would shape future military aircraft design. The F3D's power distribution system supported multiple radar units and electronic warfare equipment through an integrated network. The architecture handled substantial power requirements for the vacuum tube-based radar systems. Subsequently, the power management system evolved to accommodate additional electronic warfare equipment in later variants. The power system featured dedicated circuits for each radar component, ensuring operational stability. Hence, the AN/APQ-35 radar system received a consistent power supply despite its high energy demands. The architecture incorporated protective measures against power surges and electromagnetic interference, crucial for maintaining electronic system reliability. The F3D2Q variant, later redesignated as EF-10B, established itself as a pioneering electronic warfare platform. These modified aircraft conducted the first USMC airborne radar jamming mission on April 29, 1965. The F3D Skyknight possessed an array of advanced electronic warfare capabilities that made it a formidable asset in aerial combat. It excelled in collecting signal intelligence and communications intelligence, allowing it to intercept and analyze enemy communications. Additionally, it was adept at gathering electronic intelligence, providing crucial insights into enemy radar systems and their operational characteristics. The aircraft was equipped with high-powered electromagnetic jamming technology, enabling it to disrupt enemy radar systems effectively. Furthermore, it featured sophisticated spoofing mechanisms designed to deceive and confuse enemy fire control systems, significantly enhancing its survivability and mission success rates. The EF-10B continued these vital electronic warfare missions until October 1969. Accordingly, these operations proved essential in suppressing enemy air defenses and protecting Allied aircraft. System reliability remained paramount in the F3D design philosophy. Therefore, critical electronic systems incorporate redundant components to ensure mission success. The aircraft featured backup systems for essential functions, with no single component failure capable of causing catastrophic results. The maintenance program focused on ensuring electronic system reliability through intensive preventive measures. PCBA, or printed circuit board assemblies, underwent rigorous cleaning procedures to prevent contamination-induced failures. These assemblies met the stringent IPCA 610 Class 3 standards, the highest requirement for military applications. The F3D electronic systems underwent continuous improvements throughout its service life. Undoubtedly, this commitment to system reliability established new standards for naval aviation electronics. The aircraft's electronic warfare capabilities proved particularly valuable in combat operations, where system dependability directly impacted mission success rates. F3D performance engineering. Straight-wing design characterized the F3D Skyknight's aerodynamic profile, prioritizing stability over high-speed performance. First of all, this conventional configuration enabled superior turning capabilities compared to swept-wing fighters, allowing the F3D to outmaneuver MiG-15s in combat scenarios. The F3D-2's design emphasized operational effectiveness over aesthetic appeal. In essence, the aircraft achieved a maximum speed of 585 knots at altitude and maintained a service ceiling of 36,700 feet. The bulky fuselage, primarily shaped by radar system requirements, housed substantial internal fuel capacity, enabling a combat radius of 500 nautical miles. With external fuel tanks this way, the F3D underwent significant engine development iterations. The aircraft was powered by twin Westinghouse J-34 36 engines, which delivered remarkable performance tailored to its operational needs. Each engine produced an impressive 4,600 pounds of thrust, providing the Skyknight with the power necessary for demanding missions. This configuration enabled a climb rate of 3,570 feet per minute, showcasing its ability to reach operational altitudes quickly. Together, the engines represented a significant improvement in thrust and performance over earlier variants, solidifying the aircraft's reputation as a capable and reliable platform in combat scenarios. Primarily designed for the more powerful J-46 engines, the F3D-2's enlarged nacelles ultimately housed uprated J-34 38 engines. This configuration enhanced overall performance, though the aircraft never achieved its full potential due to the J-46 program's cancellation. The F3D-2 incorporated advanced flight control innovations to enhance maneuverability. A sophisticated spoiler system complemented the traditional ailerons, markedly improving roll response. The control stick featured an automatic mechanical advantage shifter, providing a 2:1 ratio for boost-off flight scenarios. The aircraft's stability characteristics demanded careful attention during carrier operations. The F3D-2 required stronger catapult bridles than contemporary fighters, and its landing gear system needed precise shock absorber tuning to manage arrested recoveries effectively. The addition of an autopilot system further enhanced flight control precision. At operational altitudes, the F3D-2 demonstrated remarkable stability across its speed envelope. The aircraft maintained controlled flight at both extremes of its performance range, offering pilots predictable handling characteristics essential for night operations. This stability proved particularly valuable during radar intercept missions, where precise control facilitated successful target engagement. Combat Systems Engineering. Armed with 4 powerful 20 mm cannons, the F3D Skyknight demonstrated remarkable weapons integration capabilities that set new standards for naval aircraft. The aircraft's combat systems engineering focused primarily on achieving superior night fighting capabilities through advanced weapons and fire control integration. The F3D weapons integration presented unique engineering hurdles. Engineers faced the task of incorporating both conventional cannons and experimental missile systems. Following successful testing, one XF3D-1 underwent modifications in 1950 to carry and fire for Sparrow I missiles. This advancement made the F3D-2M the first U.S. Navy jet aircraft equipped with operational air-to-air missiles. The weapons payload of the F3D Skyknight was designed for versatility and power. It was equipped with 4 20 mm cannons, each featuring a high ammunition capacity to sustain prolonged engagements. The aircraft could also carry up to 4,000 pounds of bombs, enhancing its effectiveness in ground attack missions. Additionally, it was fitted with integration points for the Sparrow I, Roman II and Roman III missiles, expanding its capabilities in air-to-air combat. Its compatibility with the Meteor missile further enabled extended-range engagements, solidifying the Skyknight as a formidable multi-role fighter. The Westinghouse and APQ-35 fire control system represented a significant engineering achievement. The APG-26 gun-aiming radar, effectively operational up to 4,000 yards, provided precise targeting capabilities. The system featured an innovative C-scope display on the pilot's front console, enabling accurate fire control without visual contact. The fire control system incorporated sophisticated target acquisition features. First, the radar operator could maintain manual tracking or engage the automatic lock function. Soon after target acquisition, the system displayed a countdown range dial, allowing pilots to open fire within optimal engagement distances of 500 to 1,000 meters. Combat effectiveness data validated the F3D engineering design choices. Essentially, the Skyknight achieved 6 confirmed kills during the Korean War, including 1 Polikarpov Po-2, 1 Yakovlev Yak-15, and 4 Mi-G-15s. The aircraft's first combat victory occurred on November 3, 1952, when a Barrier low-cap aircraft successfully intercepted a communist jet fighter. The F3D combat systems proved particularly effective in night operations. Generally, the aircraft conducted successful patrols over northern Korea, establishing complete dominance in nighttime engagements. The effectiveness of these systems led enemy forces to develop specific countermeasures, including 4 aircraft teams guided by ground controllers to challenge F3D operations. The engineering team continuously refined the combat systems based on operational feedback. The F3D2 variant incorporated an improved Westinghouse and APQ-36 fire control system, simultaneously enhancing target acquisition and engagement capabilities. These improvements, coupled with the aircraft's stable platform characteristics, enabled the F3D to maintain its combat effectiveness despite its relatively modest speed and climb rate performance. Engineering for maintainability. Maintenance engineering played a pivotal role in shaping the F3D Skyknight's design philosophy. The aircraft's maintenance requirements primarily stemmed from its complex vacuum tube-based radar systems, which demanded intensive upkeep to maintain operational status. First and foremost, the F3D's design incorporated strategic access points throughout the airframe. The aircraft featured a large equipment bay in the fuselage, accessed through a belly door spacious enough for technicians to stand upright. This innovative approach to maintenance access reflected a departure from conventional fighter designs of the era. The escape system design exemplified this philosophy through an unusual configuration. Rather than traditional ejection seats, the aircraft utilized an inclined tunnel behind the cockpit. This design choice necessitated careful consideration of access panel placement for both maintenance and emergency scenarios. The F3D's engine configuration demonstrated exceptional forethought in modular design. The twin Westinghouse power plants could be easily accessed and dropped out for replacement through a straightforward procedure. This modular approach proved invaluable for carrier-based operations, where rapid engine maintenance could significantly impact operational readiness. The architecture of the radar system introduced a series of unique challenges due to its complexity. The APQ-35 radar was composed of multiple components, including separate radar dishes assigned to specific functions. Each radar type operated with its transmitter, ensuring precise performance tailored to its role. Additionally, the system required dedicated control systems and displays for effective operation, adding to the intricate design and operational demands of the technology. The complexity of the F3D's systems demanded comprehensive field maintenance protocols. The vacuum tube-based electronics required regular attention, with technicians performing intensive maintenance routines to keep the radar operational. At the same time, the aircraft's dimensions posed challenges for carrier deck crews, occasionally resulting in minor handling damage. The maintenance program evolved to address specific operational challenges. Evidently, the wooden carrier deck required protection from the engine exhaust, which could ignite flammable materials. The bridle system, connecting the nose wheel to the catapult, demanded stronger construction than contemporary fighters, necessitating careful maintenance and inspection procedures. The F3D2 variant introduced additional maintenance considerations. The uprated J-34 engines required modified maintenance protocols, certainly impacting the aircraft's serviceability. The enlarged nacelles, originally designed for the J-46 engines, created new access points that maintenance crews needed to familiarize themselves with. The aircraft's training requirements extended beyond flight crews to maintenance personnel. Indeed, the sophisticated radar systems demanded specialized knowledge, leading to the development of dedicated maintenance training programs. This approach ultimately improved the aircraft's operational readiness and combat effectiveness. Evolution of the F3D platform. Throughout its operational history, the Douglas F3D Skyknight underwent numerous engineering refinements, transforming from a dedicated night fighter into a versatile platform for advanced aviation technologies. The F3D's development began with 3 XF3D prototypes, followed by 28 F3D1 aircraft and the more capable F3D2 series. Firstly, The F3D2 variant incorporated substantial improvements, primarily focused on enhanced engine performance and avionics capabilities. The aircraft received uprated J-34 W-36 engines, an autopilot system, and advanced gun-laying radar. Wing modifications proved crucial in addressing early performance limitations. The F3D2 introduced wing spoilers to increase roll rate, alongside existing ailerons. Ultimately, these modifications enhanced the aircraft's maneuverability, crucial for its night fighting role. As time progressed, the F3D platform demonstrated remarkable adaptability. The F3D-1M and F3D-2M variants pioneered air-to-air missile integration, becoming the first U.S. Navy jet aircraft fitted with operational Sparrow I missiles in 1954. These modifications required removing the 20mm cannons and installing a longer nose section to accommodate the missile control system. The platform's evolution reached its pinnacle with the EF-10B variant. These modified F3D2s served as electronic reconnaissance and countermeasures platforms during the Vietnam War. The spacious fuselage proved invaluable for housing sophisticated electronic warfare equipment, enabling the aircraft to perform critical jamming missions against enemy radar systems. Primary technical challenges centered around engine performance and carrier operations. Originally designed for more powerful J-46 engines that never materialized, engineers adapted the airframe to accommodate improved J-34 variants. The aircraft's size created notable challenges for carrier operations, requiring adjustments to standard procedures. Its unconventional dimensions made deck handling more complicated, while its increased weight posed difficulties for existing catapult systems during launch. Additionally, the thermal output from its engines presented issues for wooden deck surfaces, necessitating careful management to prevent damage during operations. The Marines recognized the F3D-TK's potential despite these limitations. The aircraft found its true calling in Marine Corps service, where its two-man crew concept and night fighting capabilities proved particularly valuable. The platform's stability and size, initially seen as drawbacks, became advantages for testing advanced systems, including automatic carrier landing capabilities. The F3D-TK's career extended well beyond its intended lifespan through continuous adaptation. Its size and relative simplicity made it an ideal testbed for various experimental systems. The aircraft supported development programs for multiple air-to-air missile systems, including Sparrow I, Roman II, Roman III, and Meteor missiles, establishing new capabilities for naval aviation. Engineering legacy of the Skyknight. The Douglas F3D Skyknight's engineering achievements shaped military aviation development for decades after its introduction. Primarily designed as a night fighter, the aircraft's innovative features influenced numerous aspects of naval aviation technology and doctrine. The F3D-TK's side-by-side cockpit configuration established new standards for crew coordination in naval aircraft. Analogous to this design philosophy, numerous subsequent aircraft adopted similar layouts for missions requiring intensive crew interaction. The Skyknight's successful carrier operations, in light of its substantial size, proved that larger aircraft could effectively operate from carrier decks. The aircraft's modular design approach influenced future naval aircraft development. Previously unseen in carrier-based aircraft, this configuration allowed for rapid component replacement and simplified maintenance procedures. The F3D-TK's successful integration of multiple radar systems in a carrier-based platform established design principles that guided the development of subsequent all-weather fighters. The F3D Skyknight introduced groundbreaking technological advancements that had a lasting impact on naval aviation. It became the first operational carrier-based jet specifically designed for night fighting, setting a new standard for all-weather combat capabilities. It was also the first Navy jet to be equipped with fully operational air-to-air missiles, marking a significant evolution in aerial weaponry. Additionally, it was the first aircraft to successfully demonstrate radar-guided missile systems, showcasing the potential of advanced targeting technology in modern warfare. The Skyknight played a crucial role in developing the AIM-7 Sparrow missile family, contributing to air-to-air missile advancement. The F3D-2M variant became the first Navy jet aircraft fitted with operational Sparrow-I missiles in 1954, establishing new capabilities for naval aviation. The aircraft's electronic warfare capabilities proved groundbreaking. Formerly designated as F3D-2Q and later EF-10B, these modified aircraft conducted the first USMC airborne radar jamming missions. Their success in electronic warfare operations established new doctrines for aerial electronic combat. The Skyknight's operational history provided valuable insights for naval aviation development. The aircraft's stability and spacious fuselage made it adaptable to various roles, demonstrating the importance of flexible platform design. This adaptability allowed the F-3D to serve effectively from the Korean War through the Vietnam conflict, ultimately becoming the only jet fighter to operate in both wars. The F3D radar integration experience highlighted the importance of comprehensive operator training. The initial lack of specialized radar system training led to the development of more structured training programs for complex avionics systems. These lessons influenced future naval aviation training protocols. The aircraft's carrier operations revealed crucial design considerations. The challenges faced with deck handling and catapult operations informed future large aircraft carrier integration. The F3D experience with wooden deck thermal management issues led to improved protection measures for carrier operations. The Skyknight's electronic warfare success established new paradigms for aerial combat. Its effectiveness in jamming enemy radar systems demonstrated the growing importance of electronic warfare in modern combat operations. This legacy continues to influence modern naval aviation doctrine and aircraft design. The F3D's role in missile development proved particularly significant. Its stability and size made it an ideal test platform for various missile systems, including Sparrow-I, Roman II, Roman III, and Meteor missiles. These development programs established fundamental principles for integrating guided weapons with carrier-based aircraft. The aircraft's influence extended beyond its operational life through its contributions to automatic carrier landing system development. This technology, tested on the F3D platform, became crucial for modern carrier operations. The lessons learned from these trials influenced the development of subsequent carrier-based aircraft landing systems. The Douglas F3D Skyknight is not just an aircraft, but a symbol of innovation in aviation technology in the 1950s. With its groundbreaking design, advanced radar integration, and powerful electronic warfare capabilities, the Skyknight completely changed the standard of naval aviation. Its flexible adaptability from night combat to electronic warfare platforms demonstrates excellence in military technology development. The Skyknight's legacy continues to have a profound influence on modern aircraft design and combat tactics. Do you think the Skyknight's technologies are still relevant in modern combat? Share your thoughts in the comments. Thanks for watching.